section 8.3, starting on page 182 of your notes packets, and we're looking at hyperbolas. So if you'll think back to section 8.1, hyperbolas are the third type of conic section, and you actually see both parts of the cones within a hyperbola. Okay, a hyperbola has two pieces, and it's kind of shaped by this box and asymptotes. So you have the vertices going off in two different directions from each other, boxed in by these asymptotes, and then our A and B are these distances that form our box, okay, our central box. So hyperbolas with a center HK. As usual, the center is in the middle here, HK. The equation is x minus h squared divided by a squared minus now y minus k squared divided by b squared equals 1. The difference between a hyperbola and an ellipse is that subtraction sign. So y minus k squared divided by a squared minus x minus h squared divided by b squared equals 1. And again, very similar to an ellipse except for that minus sign. Focal axis again, y equals k and x equals h. Foci, still h plus or minus c comma k, and h comma k plus or minus c. Vertices, still h plus or minus a comma k, and h comma k plus or minus a. Let's slide this down here. Okay, so now we have different terms for our axes. We have our semi-transverse axis, A, and our semi-conjugate axis, B, playing the same roles as our semi-major and semi-minor axes. And the Pythagorean relation now is back to the one that we knew before. C squared equals A squared plus B squared. C squared equals A squared plus B squared. Because now our focus is further away from the center. So if this is A, this distance here is A, this distance here is B, we have our focus on the outside, and that whole distance is C. So C is, once again, our longest distance. And we have our asymptotes here, the dashed lines that are found by y equals plus or minus b over a times x minus h plus k. It's a line with the slope of plus or minus b over a. So this would be the positive slope and the negative slope. And then we have x equals plus or minus a over b times y minus k plus h. Below the table, we have our diagrams. So if our transverse or our semi-transverse axis is horizontal versus vertical. All right, so let's look at what we can do with it. All right, looking at example 1, we want to find the vertices and foci of the hyperbola. Just like with the ellipse, we want to make sure that this equals 1. So we're going to divide by 36. So we get x squared divided by 9 minus y squared divided by 4 equals 1. So this tells me that a squared is 9, so a is 3. B squared is 4, so b is 2. And we want to find c. C squared equals a squared plus b squared, which is 9 plus 4, which is 13. So c equals plus or minus the square root of 13. So what this tells me is that once again, our major axis or our transverse axis is in the x direction. So vertices are at plus or minus 3 comma 0, and our foci are at plus or minus square root of 13 comma 0. So what this looks like now when I graph it, 1, 2, 3, 1, 2, 3, and 1, 2, 1, 2. So here is kind of the box, and that means that my asymptotes go from the center out through each of the corners of the box. My vertices are here, my foci are just outside of them, and my hyperbolas go from the vertex along the asymptotes. There we go. Sorry, that went through a focus. It should have gone through the vertex. Remember, each of these is actually 2 points, so your vertices are 3, 0 and negative 3, 0, and square root of 13, 0, negative square root of 13, 0. That's how we have 2 points for each vertex and focus. Our next objective is to graph hyperbolas, find the equation of a hyperbola satisfying given conditions. So in example 2, we want to find the equation of a hyperbola with foci at 0, -3 and 0, 3, whose conjugate axis has a length of 4. So if I sketch this right here, 0, -3, and 0, 3, those are foci, so our graph does not actually go through those points. With a conjugate axis with a length of 4, so 2, 2, that means our transverse axis is the y-axis, meaning we are centered at 0, 0. Now, again, our hyperbola doesn't go through any of the points that are listed right now, but we do know that if the distance from the center to the focus is 3, c equals 3, and because the conjugate axis is a length of 4, so the center to one of the ends there, b, is 2. So we can find a. C squared equals a squared plus b squared. So 9 equals a squared plus 4. A squared is 5, so then a is plus or minus the square root of 5. And again, we just choose the positive value. So we say a equals the square root of 5, which is just less than between 2 and 3. So if I draw my little hyperbola box, and out from the center come my asymptotes. So here is the hyperbola. Okay, there's the hyperbola. Now the equation of the hyperbola, 1 equals, and it always equals 1, so we might as well start with the 1 equals. Our major or our transverse axis is the y-axis, so we start with y squared divided by a squared, which is 5, minus x squared divided by b squared, which is 4. There is the equation. To confirm this with our graphing utility, we have to then solve it implicitly for y. So if we're solving this implicitly for y, we're adding this to the other side. So y squared over 5 equals 1 plus x squared over 4. Multiply by 5. Y squared is 5 times the quantity of 1 plus x squared over 4. So then y equals the two equations, plus or minus the square root of 5 times the quantity of 1 plus x squared over 4. And if we put this into our graphing calculator, we will get this hyperbola, which matches our sketch. Examples 3 and 4 follow the same equations and the same steps that we've been using for the other conic sections, so go ahead and try those on your own. After example 4, now we'll look at eccentricity of a hyperbola. Remember, we looked at eccentricity of an ellipse, and it's talking about how skewed is it, how much different is it from a circle. So again, we're looking at how stretched does the hyperbola look. Okay, in this case, we have E equals C over A, where C is now the square root of A squared plus B squared over A. A is the semi-transverse axis, B is the semi-conjugate axis, and C is the distance from the center to one of the foci, so either focus. In example 5, we're looking at a comet that follows a hyperbolic path about the sun that has a perihelion. What that means is the distance between the focus and the vertex. So the distance between the focus and the vertex is 90 gigameters. And gigameters, remember, are a unit that we used to measure the orbit of the Earth around the Sun. When the line from the comet to the Sun is perpendicular to the focal axis of the orbit, the comet is 281.25 gigameters from the Sun. Calculate A, B, C, and E. What are the coordinates of the center of the Sun if we coordinatize space so that the hyperbola is given by this? Okay, a couple things to notice. First of all, we have an x squared and a y squared. X is our transverse axis, and then y will be our conjugate axis. So if I'm drawing this, it would be something like centered at h is 0, k is 0. So I'll center it at 0, 0 with, we're not really sure the dimensions of our box at the moment, but we'll just do this. This is the general shape of any hyperbola, right? And I know that x is my transverse axis, so it's going to look something like this, where the Sun is the focus of this arch of the hyperbola. So here's the Sun at the coordinate c, 0. And what we know is that the distance between the Sun and the hyperbola is 90 gigameters. So this distance right here is 90. Okay, and then we also know when the line from the comet to the Sun is perpendicular to the focal axis. So if we were to draw a line perpendicular here, at that point, the comet is 281.25 gigameters from the Sun. Okay, so we know that this has an x value of c and a y value of 281.25. So c, 281.25, which means that if I put c into our equation, I should have a value of 281.25, right? This is the same as c, f of c. Okay, so using that knowledge, we can substitute c here. C squared divided by a squared minus y squared over b squared equals 1. So we've just substituted c for x. And then solving for y, I find that, so if I subtract the fraction by adding it and then subtract 1, so y squared over b squared equals c squared over a squared minus 1. Multiply both sides by b squared. Y squared is b squared times, I'm going to rewrite c squared as a squared plus b squared so that we only have two variables here, divided by a squared minus, and rewriting my 1 as a fraction of a squared over a squared. So then y equals plus or minus the square root of b squared times, they have a common denominator, so a squared minus a squared is 0. B squared over a squared. So I have that y equals plus or minus, it should be a squared. Y equals plus or minus the square root of b squared times b squared is b squared, divided by the square root of a squared is a. And this equals 281.25. Okay, so what that means is that if I have b squared, it equals 281.25 times a. Okay, so now I'm going to go ahead and use this equation to substitute b squared for, if I have c squared equals a squared plus b squared, then b squared is c squared minus a squared. So I'm going to bring this up here and say c squared minus a squared equals 281.25 0.25a. And then I know that c minus a is 90 from our perihelion distance. C minus a equals 90. So then c equals 90 plus a. So I'm going to substitute that here. Then I'll have an equation with just one variable. So 90 plus a squared minus a squared equals 281.25a. When I have a binomial squared, I have to distribute. So 90 times 90 is 8100, plus 90 times 2 is 180a, plus a squared minus a squared equals 281.25 times a. The a squareds will cancel out. So I have 8100 plus 180a equals 281.25a. Subtract the 180a from both sides. 8100 equals 101.25a. Dividing both sides by 101.25, I get that a equals 80. Substituting that in, c minus 80 is 90, so c is 170. And lastly, substituting for b, and you can substitute here, or down here, okay? Either way, so we'll do that b equals the square root of 281.25 times 80, which gives us, so I substituted into this equation down here, which gives us a b value of 150. Okay, now we found a, b, and c. We have to find e. E equals c over a. So that's 170 over 80, which is 2.125. So we have A, C, B, and E. That puts us, if C is 170, the sun is at 170, 0. All right, looking back at the question, let's make sure we answered all the parts. We have our comet. We used all of this to find our coordinates. Calculate A, B, C, and E. Good. What are the coordinates of the sun if we coordinatize the space? Okay, so that answers the question. On the next page, looking at example 6, I'll start setting it up with you and then let you finish. So example 6, radio signals are sent simultaneously from transmitters located at points O, Q, and R. R is 100 miles north of O, and Q is 80 miles due east of O. So we have this point O, and R is 100 miles north. So we know this distance is 100. We have Q 80 miles east. This is 80 miles to Q. The low RAN, which is long range navigation receiver on Sloop, which is like a ship, Gloria receives the signal from O 323.27 microseconds after the signal from R and 258.61 microseconds after the signal from Q. What is the sloop's bearing and distance from O? Okay, so the signal between O and R is 323. So from O to G minus R to G, the difference in the time that it took to travel these two distances is 323.27 microseconds. And from O to Q, OG and QG. So OG minus QG equals 258.61 microseconds. Okay, now what we have to recognize is that microseconds is not a unit of distance. So a couple of things that you need for this problem is to know that the Lorentz system conversion is 980 feet per 1 microsecond. And then if you'll recall, the conversion from feet to miles is 1 mile to 5,280 feet. Okay, if we run this conversion, we will find that the distance here is 60 miles. So the difference in distance from Gloria to O and R is 60 miles. And then similarly, we're going to run the conversion here. And when you put it into your calculator, you will find that this is 48 miles. Okay, so what this tells us is we have this 60 miles is our major axis. So we can say, working with system 1, we're looking at a hyperbola where 60 equals 2a, and we know that the distance between O and R is 100, so that equals 2c, and we can say that our center of our hyperbola is about halfway between O and R, so that exactly halfway, so that's 50. So we can say our center is at 0, 50. A equals 30 and C equals 50. All right, so from here you need to find the value for B and substitute it into the standard form of the equation, and then do the same thing for the second equation. And what you're looking for is where G is, so where those two hyperbolas cross must be the location of Gloria. When you finished example 6, we'll take a look at example 7. Our objective is to solve systems of nonlinear equations. So similar to one that we've seen before, we want to find the intersection points of these two graphs. So taking a look at the first equation, notice the subtraction sign. That means that this is a hyperbola where a squared is 4, so a is 2. And b squared is 25, so b is 5. And the second equation, notice the addition, is an ellipse, where a squared is 25, so a is 5. And I'm going to put a little x, so I know that's going along the x-axis. And then b squared is 4, so b is 2, and that's going in the direction of the y-axis. So, and then similarly over here, this is x and that's y. So when I sketch my graph, I want to make sure to give myself enough space to go up to at least 5. So 1, 2, 3, 4, 5, 6, 7, 8. All right, I'll start with the hyperbola. So in the x direction, I go 2. I'm drawing my little box. In the y direction, I'm going 5. And then I will sketch in my asymptotes. Okay, now I put my vertices in and sketch the hyperbolas, both arms of the hyperbola, singular hyperbola. Okay, so that's a sketch of my hyperbola. Now for the ellipse, my major axis, 1, 2, 3, 4, 5, 2, 5, 2. There we go. So what I'm looking for is the points of intersection. 1, 2, 3, 4 points of intersection. Okay, and I'm going to do this in a black pen. So in order to find those points of intersection, I'm going to use my graphing calculator. And in order to graph this, that means I need to put it into explicit form. So I need to solve for y. So I will start by subtracting 1 and adding y squared over 25 to both sides. So I have y squared over 25 equals x squared over 4 minus 1. Then multiply both sides by 25. So y squared is 25 times the quantity of x squared over 4 minus 1. And then the square root. So I end up with two implicit equations of 25. So plus or minus the square root of 25 times x squared over 4 minus 1. That's my first pair of equations. And then for the ellipse, I'm doing the same thing, except I'm just going to subtract the x squared over 25. So y squared over 4 equals 1 minus x squared over 25. Multiply both sides by 4. Y squared is 4 times the quantity of 1 minus x squared over 25. And then square root. Y is plus or minus the square root of 4 times the quantity of 1 minus x squared over 25. Now when I put that in the calculator, I will have 4 different equations to put in. All right, once again, it looks like there are some gaps in my graph. However, I know that there shouldn't be. So if I zoom in, and I'll zoom into the origin, you can see that those gaps are getting smaller, and really they're not there. That's just the accuracy of the calculator. It's not exactly something that we have to worry about. It's just something that you need to be aware of. So even if it looks like there's a gap, it's not a gap, it's just the accuracy of the calculator. What we're looking for are these 4 points of intersection. Now, because both hyperbolas and ellipses have 2 axes of symmetry, as soon as I find one of those points, I actually have the coordinates for all 4. So we're going to second calculate the intersection, option 5, and we're going to see if we can locate our first curve. So see the little spider is there. Going over to that point of intersection, enter, 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 making sure that it's there the whole time. So this point here has the coordinate 2.13, comma, negative 1.81. Now using symmetry, I know that this will then have the negative x value, so negative 2.13, comma, negative 1.81. Negative x and a positive y, so negative 2.13, comma, 1.81. And positive for both, 2.13, comma, 1.81. So those 4 points are the solution to the system of equations. All right, that's the end of section 3, and in fact all of chapter 8. So reflect over this section, and then on the bottom of the next page, make sure you write and summarize what you learned from this lesson.